Hello, everybody. So what we're going to be looking at today is section 6.5 in your book, which is divergence and curl. So these are two new operations that we're going to perform on vector fields. And so we'll go ahead and just jump into it here. Okay. So the first topic we're going to talk about is divergence. So divergence. Okay. So the divergence of a vector field. So let me write it. The divergence of a vector field evaluated at a point is basically it's a number that will tell you how much fluid is leaving that point or entering that point. So I'll say it is the, let's say, um, outflow of fluid at that point. And that's only going to be true if the vector field was, the velocity of a fluid flow at a point. Yeah. So what did I write so far? The divergence of a vector field evaluated at a point is the net outflow of the fluid at that point. And that's if, F is the velocity field of a fluid. Okay, and there's a couple of pictures that will make this make more sense. So examples. Well, come on, just let me draw a line. Okay, thank you. So for example, all right, something like this. Um, Hopefully you can see that at the center here, you've got like vector field lines heading out from the center, right? That would be a positive divergence at that center. So positive divergence. And that's because if you look at the flow lines, it looks like liquid is flowing out of the center point. I'll say fluid flows out of 0, 0, right? Nothing is heading in to 0, 0, only out of 0, 0. Whereas if you take kind of the opposite kind of shape, where if you've got your field lines all flowing into a point, right? That would be negative divergence where you have fluid flowing into a point. Okay. So that's what we're talking about when we're talking about divergence. And so um, there would be vector fields that had zero divergence as well. That would be if the flow is just not um, creating fluid or getting rid of fluid, which is kind of what's happening here, right? Like if you were looking at this, like you could think of this like being like a broken sprinkler, right? Or like a hose just lying on the ground, where at this point, in order to get this kind of velocity field, there would be liquid being produced right here at this point and just flowing out. Whereas in order for this to happen, this would be like a hole, and then like liquid flowing down into the hole. Okay, so that's the kind of fluid interpretation of these things, right? So positive divergence, it's like creating fluid out of nowhere. Whereas a negative divergence, it's like fluids flowing into this point and then disappearing. Okay, so that's kind of the idea of divergence. You could also have divergence that's zero, and that would just be if, like a normal like fluid could be flowing in some direction, but not like being created or like destroyed here. So like if I just make a simple vector field where just like, well, fluid's just going up and to the right. That might be zero velocity, zero divergence. That's not the only picture for zero divergence, but it's just one interpretation, right? You don't obviously, at least when you're looking at this third picture here, it doesn't have this kind of thing where a bunch of lines are leaving from a certain point or a bunch of lines are converging at a certain point, right? This is just up and to the right, up and to the right, up and to the right. Okay, so that's kind of what we're talking about when we're talking about divergence. And then the question will be, how do you calculate it? Okay, so I didn't, I'll have to write the definitions here. So definition. Definition. So if we're going to be looking at a 3-component vector, I mean, you could do it for a 2-component vector. P, Q, R. And you need these partial derivatives to exist. Px, Qy, Rz. Then the divergence of F is, here you go. So you write it div F for divergence F. And then what it is it's just Px plus Qy plus Rz. Or, if you want to write it in the other notation for the derivatives, you could write it as partial P with respect to X, partial Q with respect to Y, partial R with respect to Z. Okay? Now, this looks very similar to what you've seen before in terms of the gradient, but don't mix them up. Okay? So don't mix this up with the gradient. So the gradient of F would be grad F. We write it with this symbol, grad F, and that is the vector where you'd have Px, Qy, Rz. The divergence of F has the same pieces, Px, but it's Px plus Qy plus Rz. Right? So you see the difference, right? The gradient of F is a vector. The divergence of F is a single number, and that single number represents what we said it did, like the amount of outflow at a particular point. Now, one thing you might notice about this is that this is a vector, this is a constant, but what they'll do is they'll use this notation for it often. They'll write it like this, grad dot F. They write it like that. And the interpretation of this is, well, that notation is really an abusive notation, but they use it anyway. So this notation for div F, which is grad dot F like that, is, what we call an abuse of notation. You probably haven't heard that very much in your like mathematical career yet, But stuff like this happens in math a lot, where um, this is not a real dot product, but it kind of reminds us of a dot product. So we use the notation for a dot product, even though it's not really a dot product. Okay. So this is an abusive notation because this is not a real dot product. But they use this notation because if you write grad dot f like this, and you think of the gradient symbol, if you think of the gradient symbol as being d dx, d dy, d dz, like this, and then you think of f as being p q r, like that, then when you do a dot product, you multiply like first component, second component, third component, and third component. And if you do that here, you'd have ddx p plus ddyq plus ddz r. So it feels like this is the right notation, but it's not, because this is not a real vector, because these aren't numbers. But this isn't really a vector because those aren't numbers in there. So technically it's not a real dot product. So this is not a real dot product. Okay, but they will still use this notation. They will still use this notation for it in the book, and so you need to be aware of it because it kind of acts like a dot product. Okay, now having done that, these are really easy to calculate. There is nothing to them, and you should feel free to use a computer to help you with the derivatives if you want. So here's an example of one. So let's just say if f equals e to the x yz negative y squared, find divergence f evaluated at 0 to -1. And so they ask for it evaluated at points sometimes, not always. But I am on this one. So what would we have to do? So, first just compute divergence f, which it's not complicated here. Remember, what you do is you've got three components, or two if you've got a two-component vector, but you just do partial with respect to x of the first thing, partial with respect to y of the second thing, partial with respect to z of the third thing, and that's your divergence. Or you could write it this way as well. And then you just do these derivatives. So d dx e to the x is e to the x. d dy yz is just z. ddz of -y squared is 0. So you get that. And then here they asked us to plug in a point. So I'm going to evaluate at 0 to -1. So you could write that a lot of different ways. I'm using the other notation. I'm just switching between them whenever I feel like it. We're just going to plug 0 to -1 into the formula that we've got here. So just e to the 0 plus -1 for z, and that's it. So what do we get? 1 minus 1. So I guess we just get 0 at this point. Wait, Did I put in the wrong numbers? Hold on. Oh no, I didn't put in the wrong numbers. They just did the problem wrong in the book. That's all. Yeah, okay. I was confused for a second there. I'm like, they got a completely different answer, and I'm like, what's going on? And it's because they have, oops, they didn't have negative y squared here. They had negative y z squared. Actually, no, they had positive y z squared. No, negative. It doesn't matter though. Anyway, they had the wrong answer. That's what's important. So for us, we got the divergence is zero. Okay. And your interpretation of that would be uh, if f is fluid velocity at the point 0 to negative 1, the same amount of fluid is flowing in as is flowing out. Right? So you got this point, and you have like some fluid flowing in, and then you also have some fluid flowing out. And the amount that goes into that point and the amount leaving that point is the same. And that's why this comes up zero. Okay. So that's just an interpretation. They didn't ask for an interpretation, but we're just saying it. Okay. Same amount of fluid flows in as flows out. Okay. Yeah. So then there's kind of two interpretations of a zero divergence. So let's write them. Okay. So we know that if div f, which is grad dot f, equals zero, that the amount of fluid flowing into a point equals the amount of fluid flowing out. So fluid in equals fluid out. Okay, that's what zero divergence means. Okay, but in terms of like vocabulary around this, first thing we do is we would call it a source-free vector field. So one, uh, if div f equals zero, we call f a source-free vector field. Now, in order for that to make sense, you have to know that fluid interpretation, right? Because we know that for positive divergence, you have fluid flowing out. We would call that a source. And also, if you have negative divergence, that would mean fluid flows into a point, and we call that a sink, actually. So a source or a sink. But they're dumping them together here, and then calling, if the divergence of f is zero everywhere, we call it a source-free vector field. Okay, and that's going to be, let's see, this is going to be assuming um, f is a continuous field with continuous or with differentiable functions, component functions. So you have to be able to calculate the divergence everywhere. And also they want the domain to be simply connected. I don't know why they want the domain to be simply connected, but presumably if you've got some really weird domain for the function that maybe it screws up what they want to happen here. So source free, the divergence is zero. It's called source free. But another interpretation is going to be with something that they call magnetic field. And in a physics class, which we are not, that's why we do almost no physics. In a physics class, you'll learn that if B is usually used for magnetic fields. If B is a magnetic field, then grad dot B equals zero. Okay. So also, even though we would call it source free, you might also call one where the divergence is zero could be a magnetic field as well. So if div F equals zero, then F could be a magnetic field. So not everything is, fluid flowing places. Okay. And so those are just vocabulary words because you might take you might take do the homework problems and a problem might say, is this a magnetic field or not? And you have to understand that they just want you to find the divergence and see if it's zero or not. Okay. Let's see here. Okay. And I honestly think that's it for Divergent. So let's move on. We're going to talk about curl now. So we talked about divergence. Divergence was inflow versus outflow, right? Curl is something different. So curl, conceptually, the curl of a vector field measures basically how much the vector field is spinning at a point. Actually, that's not quite what it measures. The curl of a vector field measures um, how, let's say, an object sitting at a point would want to spin. Right. So, like, if you've got a vector field that does this, right, then obviously something right here would want to be spinning around like that, right? Does that make sense? Just based on the fluid flow lines. If you were sitting right here, like something here would just spin around in circles. Okay. And that's what you're measuring. Okay. However, the way you calculate it is like this. So let me write it. Definition. Again, we're going to need F equals, if F equals PQR in R3, and also we need PX, QY, RZ exist, then the curl of F is, so we have really interesting notation for it. We write curl F. And here is what it is. Kind of a little bit awkward to write. It is ry minus qzi plus ez. Wait, what? Okay, I'm just gonna, it's fine. Z minus Rx, J plus Qx minus Py. Gonna move this over. Oops. Oops. Third time's the charm. Qx minus Py. Okay. Okay. Or if you write it in the other notation for the derivatives, dr dy, q dz, I, plus dp dz, dr dx, j, plus dq dx, dp dy, k. So hopefully you see that this is a vector, right? Your answer is a vector here. And so we're going to have to talk about what that has to do with spinning around a point. But for now, this is your definition. So this is how you're going to calculate this thing. Let me like put it in box, make it easier to find. Okay. All right. So there's the curl of F. We also have an alternate notation for it, just like we do for the other one. We have an alternate notation just like we do for divergence. We also use curl F. We also write it grad cross F. And the reason you can use that is if you think about the cross product, because if you thought that grad cross F, if you imagine that these were vectors again, where you went I, J, K, because that's how you start out a cross product. And then your next row is grad, so that's like ddx, ddy, ddz. And then your third row is the actual PQR, and you work that out, then what you would get is the determinant of the matrix that we, not the determinant, but you would get like I and then like ddy, ddz, oops, ddz, er plus dot dot dot. I'm not going to bother writing it. But like, for example, and then if you imagine doing this right here, right, you'd get I, and then if you quote unquote multiplied these, right, it's not real multiplication, but if you did ddy of r, you would have dr dy minus, and if you quote unquote multiply these, right, you would have, this is supposed to be a z, I didn't write it very well. ddz of p would be dp dz plus dot dot dot, right? Because we have to do the other three. But you'll notice that like this one right here is this one right here, right? Wait, did I write down the wrong things? This is supposed to be a Q, right? I'm doing the cross product. So if you cross out the row and column, first column, I should have been, these are the two that I should have taken. So that should be a Q. So that should be a Q. Sorry about that. Okay. So if you write that correctly, this would be your first component, and this first component does match what you have up here, right? And the rest of them will match too. I just didn't write them there. So that's why they use this notation for the curl. Okay. Um, so yeah, and again, just like before, this is really not a determinant and that so on, right? This isn't a real cross product. It's really grad cross F is really just kind of a way to help remember how to calculate these if you forget them. Right? Just like divergence is not a dot product, curl is not a cross product. Um, Also, there's one other thing we could do. You're going to have a lot of two-dimensional vector fields. So if F is just P and Q, right? So there's no R component, um, right? So 2D instead of 3D. Then your curl F is equal to just QX minus PY. Okay. And you could figure out why that would be the case. Um, like if you put in a zero for the R, if you put in a zero for the R, then dr dy is zero because R is zero, right? So we're talking about PQR, so R is zero. So dr dy is zero because R is zero. Dq dz is zero because there are no z's, right? If we've only got two components, we're doing x's and y's, no z's. So if all there are is x and y, no z, and all there is p and q, no r, then this is zero because there's no r, this is zero because there's no z, this is zero because there's no z, this is zero because there's no r. This is not necessarily zero because q exists and x exists, p exists and y exists. So this one doesn't come up zero. So this isn't like a new definition here. This is just saying if there is no third component, then this is what curl ends up. Okay. Um, and either way, this is what you want to use for your definition, or this is what you want to use for your definition. And so what can we say about it? So first of all, it is a vector, right? Let me write this. Since curl F is a vector, right? And vectors have direction. What does the direction mean, right? Um, it has a direction. Basically, we said that we were measuring the tendency for an object to spin. Well, what's happening is that the curl F vector is pointing in the normal direction to the spinning. Okay, um, that direction is orthogonal to the spin. So like if we're looking in three dimensions here, okay, I'm not going to draw a vector field. I'm just going to draw like a point in space. So like let's say you have here, and then like let's say an object here is spinning like this. Okay, so that's like the spin. then your curl would be pointing like 90 degrees away from that. So that's what you're calculating, which is why your curl F here is pointing in the K direction when you're only in the XY plane, right? Because like if you're in the XY plane, which is like if you have X and Y, right? If you're spinning in the XY plane, then what direction is orthogonal? The Z direction, right? Which is the direction that this is pointing in. So that's why the other components go to zero. If you're just stuck in the XY plane, then you're spinning in the XY plane, but like the axis of rotation is straight up or straight down. Okay. So curl F is like the axis of rotation. Okay. So that's the idea. Um, okay. Oh, okay. Yeah. And just like we talked about um, source free and magnetic, there's another type of what's it called? Interpretation of the curl as well. That's similar. So if curl F equals zero, then F could be a gravitational field. So if curl F is zero, it could be a gravitational field. If divergence F is zero, it could be a magnetic field. Okay. Um, all right, let's calculate one. We didn't calculate any before. So let us try this. Anyway, example, let's try one. We haven't found any curl yet, so let's find curl. For F equals x squared z e to the y plus xz xyz, compute curl F. All right, so how would you do it? So your first step is you're going to start with the formula, not the cross product. You probably don't want to bother with the cross product formulation. The cross product formulation here is really just to help you remember what we wrote up here. So this is really what you should start with. Can't see what I'm circling, but now you can. Whoa, I done with the whole thing. I just wanted. Right, so start with this formula and then you just calculate the bits that you need to calculate, which are a bunch of partial derivatives. So 6 partial derivatives. It's not that bad, right? So you've got your PQR. So you got that's P, that's Q, that's R. And then we're just going to evaluate these one by one. So you need RY. So RY, derivative of R with respect to Y is XZ minus QZ. So partial here with respect to Z. Here's the only Z. So partial with respect to Z is just X. I plus, then we need PZ. Here's P. Partial with respect to Z is X squared minus RX. So partial here with respect to X will be YZ. That should have a J on it. Plus QX. Partial here with respect to X. There's only one X here. Partial is going to be Z. And py, partial here with respect to y, there is no y, so that's going to be 0. Okay, so there you go. You can leave it like that. Or if you want it in the triangular bracket notation, right, we have xz minus x, comma, x squared minus yz, comma, z. And that is curl f. So these are very straightforward in terms of, conceptually calculating these things. It's just a basic operation. It's just derivatives again, right? But there you go. So what could we say about this? Not a lot, really. You can say it's not a gravitational field, right? Because this is not a zero. So that's about all we could say. Not zero. So not gravitational, at least. Okay. Oh yeah. So here's kind of an interesting thing you can do that we haven't done. So so you could prove this. Let's see if we can. All right. So let's just do some work here. So I'll call this divergence of the curl. Okay. So suppose you compute this for just some vector field. Suppose you compute the divergence of the curl of f. I guess you could also write that as divergence is gradient dot, and then curl is gradient cross f. Looks complicated, right? You guys are doing fancy math now, aren't you? So suppose we compute the divergence of the curl. We're not going to use this. We're going to use this. Well, what happened? Okay, so we're also going to assume all the partial derivatives that are supposed to exist. Okay, so let's do that. Divergence of curl of f. So we're doing the divergence of curl f, which is the divergence of, what's curl f? Here, duplicate it. Doesn't fit. Bring it down here. I'll erase that. Move this over. Okay, I think it'll fit now. Cool. Okay, so we're doing the divergence of this vector field. Now the divergence, remember, is you do partial with respect to x of the first component, partial with respect to y of the second, partial with respect to z to the third. So there should be parentheses there, by the way. Okay, so this would be partial with respect to x, ry minus qz, plus partial with respect to y of this one, pz minus rx, plus partial with respect to z, qx minus py, like that. Let's do these partials. We'll have ryx minus qzx plus partial with respect to y here. So pzy minus rxy plus qxz minus pyz. But remember that we had a rule for mixed partials. Recall that, you know, fxy should equal fyx, and so on, right? Provided that these are continuous, right? And if you do that, what you'll see is that you've got like ryx here, but then you've got negative rxy here. So those are just going to cancel out. And then you've got negative, oops, then you've got negative qzx, positive qxz, and then you've got negative pyz, positive pzy, right? And so those are going to be equal for all the ones that I highlighted. So when you do the subtraction, everything just cancels out and you simply get 0. Okay. Okay. And then, so the divergence of the curl is 0. So the divergence of the curl is 0. Okay. Now, why do we care about that? They do kind of a weird, um, they do kind of a weird question type where they give you a vector field and they say, is this the curl of something? And you're supposed to say no or yes. Um, so like, here's a problem type. Is G equals sine X cos Y sine X, Y, Z the curl of some other vector field, right? So you have to know what the point is. And the point is that if it is, then when you do the divergence of it, it should be 0. Okay. If this is the curl of something, then the divergence of the curl should be 0. So if you take the divergence of it, it should be 0 if it's the curl. So this is the big idea. If G is the curl of something, then the divergence of G should be 0 because we know the divergence of curl F should be 0, right? So what you do is we're going to take the divergence of this vector field and see if it's 0. So we compute div G to see if it's 0. Okay, so that's all. So you just go div G equals, remember partial with respect to X of the first component, partial with respect to Y, second component, partial with respect to Z, third component. So we just do this. So partial with respect to X of sine X is cos X. Partial with respect to Y of cosine Y is negative sine Y. Here we got partial with respect to Z of sine XYZ. That's going to be cosine XYZ times the derivative of what's inside with respect to Z, which is XY. So I look at that, I say that's not 0. In general, it's not 0. So that means that G could not be the curl of any other function, of any other vector field. right? Because if it was the curl of another vector field, then we should have gotten 0, and we didn't. So those aren't hard. You just got to know what the point is. It asks if it's the curl, and you have to know to take the divergence. Um, okay, there's one more theorem, I guess. Theorem. If F equals PQR is conservative, a conservative vector field, then curl F equals 0. Okay, that's it. All right, just scrolling through here to see if I see anything worth doing. I think we're good. I'll just click through a little bit of the homework just to make sure. So I already clicked through the divergence questions. We're looking at curl. They have just calculate curl, calculate curl, calculate curl. Mostly two-dimensional vector fields. So instead of using the formula we use the one that just has one thing to calculate. Ooh, calculate the curl and plug in a point. Calculate the curl and plug in a point. Calculate the curl and plug in a point. They really like that. Calculate the curl and plug in a point. Calculate the curl and plug in a point. Give me something else. Come on. Just calculate the curl. Don't plug in the point. Oh man. Calculate the curl. Don't plug in the point. Sure. Calculate the curl. Don't plug in the point. I just want to click through a few more. Just give me a different problem type, people. Find the curl of the vector field. Yes. Oh, we're done. We're on to a new topic. Let me see. Give me a new type of question. Come on. Is the vector field conservative? How would we know? Take the curl and see if it's 0. Okay. So I'm just going to assume that that's where we end. So I guess they could do. Hold on. I'll do one. I'll do one of these. Okay. Example is F equals, ooh, complicated, 2xy sine, ridiculous, 3x squared y squared z plus 3yz squared, comma, x squared z squared cosine 3xz, comma. I'm writing this on 3 lines because of how long it is. Uh, Scroll over so I can see you. 2y sine x squared yz squared. Okay, so those three components of the vector field, and they say, is this field conservative? Right. So what do? Compute curl F. If it's 0, it's conservative. Right? So very simple conceptually. And then what's annoying is that you have to like take the derivative of this with like the product rule and stuff. So I'm not even going to do that. I'm just going to use a computer because we have not used a computer today. So how would we do this? Curl. We can type this vector field in probably however we want. I'm going to go 2xy sine 3x squared y squared z plus 3yz squared. There's my first component, comma, x squared z squared cosine 3xz, comma, 2y sine x squared yz squared. All right, so I'm just going to say curl of that vector field, and we're just going to hit enter. Wolfram knows curl. I didn't type this in the way that you normally type in vectors into Wolfram, so if it doesn't like it, we'll just retype it. Looks like it understood it pretty well. So what do we see here? So first of all, we did it. It says result. Look at that result. Is that result 0? No. So what am I going to say here? I'm going to say curl F equals something stupidly long. That's not 0. Which implies F is not conservative. The end. Okay, so that's it. So it's not conservative because if it was conservative, the curl would be 0. And that's really what you're doing here, right? So all the problems in the section are basically just what's the divergence or what's the curl. Pretty straightforward. Okay, so that's it for now. Good luck with this homework. You don't have very much left to go, right? See you next time.